In this video of our course on linear system theory, we cover chapter 9, where we start with the core of linear systems, namely state space models. As you know by now, the material of this course is kept as general as possible, and hence we will cover continuous time and discrete time systems in an equivalent way. Let's begin with continuous time state space models, which those of you who come from an engineering background are probably more familiar with. If you have a computer science background, you're probably more familiar with discrete time systems, which we will cover in the second half of this chapter. For continuous time systems, we have, as the name suggests, a continuous time variable that we call t, and which is a non-negative real number. A continuous time state space model is defined based on 4 possibly time-varying matrices, which means that these matrices can be interpreted as functions of time, and they are called the system matrix A of t, the input matrix B of t, the output matrix C of t, and the throughput matrix D of t. It's assumed that the dimensions of these 4 matrices are such that the definition of the continuous time linear state space model in equation 8 makes sense. In this definition, x of t is an n-dimensional vector denoting the state of the system. X dot of t is the derivative of x with respect to time, and x naught is the initial condition for the system, meaning that the state at some given initial time t naught is equal to x naught. Moreover, u of t is an m-dimensional vector that represents the input to the system, and y of t is a p-dimensional vector that represents the output of the system. So the way to think of the system is that the states x are internal variables of the system, which are not necessarily observable unless the C matrix, for instance, is the identity matrix and the D matrix is 0, in which case we get as an output all of the states of the system. But generally, this is not the case, and we just feed an input signal, u of t, continuously to the system, and we continuously observe the output signal y of t. What we look at next are 2 important special cases of the continuous time linear state space model. And the first one is called a continuous time linear autonomous system, and it's characterized by the fact that the input matrix B of t and the throughput matrix D of t are both 0 for all times t. So that in this case, the state space model can be written as shown in equation 9, where we observe that this type of system lacks the components with the control input u of t, and that's why it's called an autonomous system. Another important subclass of systems are called linear time invariant systems, and they are characterized by the fact that the system matrix A and the output matrix C are time invariant in the case of a linear autonomous system, and in fact also the input matrix B and the throughput matrix D are time invariant in case of the continuous time state space model. In other words, the linear time invariant continuous time state space model looks as shown in equation 10, which is very similar to equation 8, except that now the matrices are all time invariant. Going forward, it is assumed that you have some basic familiarity with continuous time state space models, or at least that you are familiar with ordinary differential equations in a vector form as they appear in the state space models 8, 9, and 10. However, no deep knowledge on state space representations will be required. It's also assumed that you have worked with the Laplace transformation before, and we'll do a quick review of the Laplace transformation on the next couple of slides. First, in 9.4, we recall the definition of the Laplace transformation. It's defined for functions f of a non-negative time, which maps into the space of m by n real matrices. The Laplace transform of f is then a function capital F that maps from the set of complex numbers into the set of m by n complex matrices, with the independent variable of the function capital F being called the frequency s, and the function value f of s being given by this integral, which involves integrating the function f of t multiplied by the term e to the minus st, and integrating this function from 0 to infinity dt. Note that due to the integration over t, the variable t drops out of this integral, and hence the integral is a function of the frequency variable s only. Again, it's assumed that you are familiar with the basic definition of the Laplace transformation from your undergraduate controls class, so the only difference in equation 11 may be that here f of t is an m by n matrix instead of a scalar function. However, this is only a minor extension because the integral in equation 11 can just be interpreted element-wise, meaning that f of s is also an m by n matrix whose elements are the Laplace transforms of the elements of f of t. Throughout the course, we shall use the following notations in the context of the Laplace transformation. First, we use a calligraphic L to denote the Laplace transform of a time function f of t, and we use the corresponding capital letter capital F of s to denote the Laplace transform of the time function f of t. Second, we use a calligraphic L with the superscript -1 to denote the inverse Laplace transform of a Laplace transform function capital F of s, which of course returns the time function f of t. Since the Laplace transformation is a bijective map, this means that there's always a unique pair of a time function f of t and a frequency function f of s, and we will use this symbol here to denote the pair f of t and f of s. Our next question is, for which functions is the Laplace transformation defined, or how do we characterize the set of functions that actually do possess a Laplace transform? And the answer is given by Theorem 9.5, which states that the Laplace integral of a time function f exists at least in some region of convergence, which is enough for our purposes if the following condition is satisfied. Namely, all of the elements fij of the function f must grow at most exponentially as time goes to infinity, which in mathematical terms means that there must exist a real constant alpha, such that each element fij of t is bounded in absolute value by the exponential function e to the alpha t, and that must hold for all times t in the positive real numbers. This condition, on the one hand, clearly means that not every time function f will have a Laplace transform, but on the other hand, this condition is not very restrictive because in reality most functions will not grow faster than the exponential function, and hence they will be bounded by some exponential function. It's actually a good exercise to look at the proof of this theorem. So we only consider the region of convergence of the Laplace transformation, which by definition is a half space that's defined by the real part of S, namely sigma, being greater than the exponent alpha of the bounding exponential function. Then, for each element fij of the function f, we will show that the integral from 0 to infinity of fij of t times e to the minus st dt is less than infinity. First, this integral is clearly less than or equal to the integral where we take the absolute value of fij of t and the absolute value of e to the minus st, where we now replace s with its definition using the real part of s and the imaginary part of s, which we can then split up further into the absolute value of e to the minus sigma t and the absolute value of e to the minus j omega t, which by Euler's formula is always equal to 1. Moreover, we can upper bound the function fij of t by our exponential function e to the alpha t. So what we obtain is that this is less than or equal to the integral from 0 to infinity of e to the alpha t times e to the minus sigma t dt. So by expressing this as the exponential function of, in brackets, alpha minus sigma times t, we can easily find the primitive of this function, which is given by 1 over alpha minus sigma times e to the, in brackets, alpha minus sigma t, where this primitive must be evaluated at the upper limit of the integral, which is infinity, minus the lower limit of the integral, which is 0. And hence, this integral will be less than infinity whenever sigma is chosen greater than or equal to alpha. As a final remark here, it should be mentioned that for the Laplace transform to exist, it's sufficient to have convergence in some half space of the complex frequency plane. Further details on this would bring us deep into the field of complex analysis, which we want to avoid at this point. Next, we also want to look at the inverse Laplace transformation, and for this we have the result of fact 9.6. So let f be a well-defined function which maps from the frequency plane into the space of complex m by n matrices, where well-defined means well-defined on some half space in the complex plane, which is bounded by a minimum real part alpha. Then the corresponding time domain function f is given by the contour integral stated in equation 12, which integrates the function capital F of s times e to the st along a contour line, which has to be chosen somewhere inside the convergence region of f of s, meaning that it's parameterized by some beta, and this beta has to be greater than the alpha which bounds the convergence region. Actually, we don't want to go into the whole business of computing contour integrals, as this is part of complex analysis. So we won't make any use of this Laplace back transformation formula in the rest of this course. However, for the sake of completeness, it's good to have seen this formula, and if you know any more about complex analysis, this formula allows you to compute the inverse Laplace transform for arbitrary functions. Instead, what we expect from you is some basic familiarity with the Laplace transformation, meaning that you're able to do basic things such as calculating transforms based on Laplace tables and also based on using the integral definition of the Laplace transformation. Moreover, you should be able to perform a partial fraction expansion for the inverse Laplace transformation and then be able to compute inverse transformations again based on Laplace tables and other basic things like this that they usually teach you in undergraduate control classes. As already mentioned, in the vast majority of cases, we use tables like this one to convert a time function into a frequency function and vice versa. Even though there are much longer and much more detailed tables available than this one, the purpose of this course is not to look at very complicated Laplace transforms, but more at the basic methods, and therefore this table here will actually be sufficient for all purposes of this course. Since it's assumed that you have seen tables like this one before, it's worth mentioning only two particular functions in this table, and the first one is this delta of t, which represents the Dirac delta function. In fact, the Dirac delta function is actually more of a distribution rather than a function, and it can be defined based on a family of distributions that we call dA of t, where a is some positive parameter, and this parameterized distribution dA of t looks as shown in this figure. In an interval between 0 and a, the distribution takes on the value 1 over a, and everywhere outside of this interval, the distribution is equal to 0. Note that the total area underneath the graph of dA of t is equal to the area of this rectangle, which is the width of the rectangle a times its height 1 over a, so it's equal to 1. Hence the integral of dA of t from t equal to 0 to infinity is equal to 1. Now the Dirac delta function is defined as the limit of this distribution dA of t where a goes to 0. Hence the Dirac delta function is non-zero only in an infinitely small interval around 0, where its function value is actually equal to infinity. However, in such a way that if we integrate the Dirac delta function delta of t from 0 to infinity, we will get to a total area of 1. The second function worth mentioning here is the unit step function, which we denote by a upsilon of t, and which simply looks as shown in this graph here. So upsilon of t is equal to 0 for all negative values of t and equal to 1 for all non-negative values of t. Some important fundamental properties of the Laplace transformation are stated in Theorem 9.7 without a proof. A, the Laplace transform is linear, meaning that if we take a linear combination of time functions, f of t and g of t, which are weighted by scalars alpha and beta, we will get in the transform domain alpha times the Laplace transform of f plus beta times the Laplace transform of g. B, integration in the time domain, so the integral from 0 to t of f of tau d tau amounts to multiplying the Laplace transform f of s by a factor of 1 over s. C, conversely, taking the derivative of the function f of t in the time domain, so df dt, amounts to multiplying the Laplace transform of f of s, by a factor s, and in addition, we need to subtract the function value of f at the point 0 plus. And D, taking a convolution in the time domain, so the convolution of two functions f and g of t amounts to taking the product of the Laplace transforms of f and g in the frequency domain. For the sake of completeness, recall that the so-called convolution of two time functions f and g, denoted as f star g, is defined as the integral from 0 to t f of tau times g of t minus tau d tau. This convolution appears quite frequently in the theory of linear systems, as we shall see when we go forward in this chapter. Very important in the context of the Laplace transformation are also the initial value theorem and the final value theorem. The initial value theorem states that if f of t is a time domain function with Laplace transform capital F of s, then the limit as t goes to 0 from the positive side, which is indicated by this 0 plus, of f of t is equal to f of 0, and that equals to the limit of the real part of s going to infinity of s times capital F of s. And similarly, the final value theorem states that if f of t is a time domain function with Laplace transform capital F of s, then if the limit of f of t exists as t goes to infinity, then this limit of t going to infinity of f of t is equal to the limit of s going to 0 of s times capital F of s. So what does the Laplace transformation have to do with the ordinary differential equations of state space models? To see this, let's first consider a system of ordinary differential equations, which is similar to that of a continuous time autonomous system. So x of t represents a time-dependent n by n matrix that must satisfy that its derivative ddt of x of t is equal to the n by n matrix A times the matrix x of t, and the initial condition for the matrix x of 0 is equal to the identity matrix. According to lemma 8.11f, we already know that the solution to this system of ordinary differential equations is given by x of t equal to the matrix exponential e to the at. Now we take the Laplace transform of both sides of equation 13, which we can do because if the time functions are equal, then also the corresponding Laplace transforms must be equal. So what's the Laplace transform of the left-hand side of equation 13? According to Theorem 9.7c, is given by s times the Laplace transform of x of t minus x of 0. And what's the Laplace transform of the right-hand side of equation 13? It's the Laplace transform of a times x of t, where by linearity we can pull the a out of the Laplace transform, and we get that this is equal to a times the Laplace transform of x of t. Now moving this term over to the right-hand side and this term over to the left-hand side, such that the two terms on the left-hand side have the common factor Laplace transform of x of t. So we can factor the left-hand side as si minus a times the Laplace transform of x of t, and what remains on the right-hand side is x of 0, which by the initial condition is equal to identity. Therefore, when multiplying this equation from the left with si minus a inverse, we obtain that the Laplace transform of x of t is given by si minus a inverse. And with x of t being equal to the matrix exponential e to the at, we get that the Laplace transform of e to the at is equal to Si minus a inverse. This expression of Si minus a inverse was introduced in the previous chapter as the resolvent of A. So what we have obtained here is summarized in proposition 9.10. For any matrix A, the Laplace transform of the matrix exponential e to the at equals to the resolvent of A, namely Si minus a inverse. At this point, you should recall from chapter 8 that Si minus a inverse represents a matrix of rational functions of S, or, as you could say, a matrix of transfer functions. And it's defined by the adjugate matrix of Si minus a divided by the determinant of Si minus a, or as you might say, the characteristic polynomial of A. So let's look at two cases where these results can actually be used to compute something. In application 1, we want to compute solutions to continuous time, linear time invariant autonomous systems. To start, consider a continuous time, linear time invariant system as shown in equation 14. As we know from lemma 8.11h, x of t equal to e to the a t minus t naught is the solution to the differential equation, which demands that the time derivative of x of t must be equal to a times x of t, with the initial condition x of t0 being equal to the identity matrix, because the solution x of t to the differential equation 15 is actually an n by n matrix. We can define the n-dimensional vector x of t as the matrix x of t times an initial condition x0, which is the initial condition of the continuous time, linear time invariant autonomous system from equation 14. Now, observe that this x of t from equation 16 is actually the solution to the state equation of the autonomous system, which can be seen by multiplying equation 15 from the right with the vector x naught, and this is what we get down here. So on the left hand side we have d dt of x of t times x naught, which is by definition x of t. And on the right hand side we get a times x of t times x naught, where again this product here is by definition x of t. As for the initial condition, we multiply this equation from the right again with x naught. Then what we get on the left hand side is x of t naught times x naught, which by definition is equal to x of t naught. And on the right hand side we get identity times x naught, which is of course equal to x naught. So in summary, the key thing to observe here is that this definition of the vector x of t leads to a solution to the state equation of the continuous time, linear time invariant autonomous system, which we have proved down here by multiplying these two equations from the right with x naught, and then realizing that this x of t actually satisfies the differential state equation and also the initial condition of the autonomous system 14a. Given that we have found such a vector x of t that satisfies 14a, it is then easy to find the corresponding output y of t that satisfies 14b. We just need to substitute the x of t that we have found into the output equation, and y of t is given by c times x of t. So we can deduce with the matrix exponential e to the at that the solution to the continuous time, linear time invariant autonomous state space model for any initial condition x naught at any time t is given by y of t equal to c times e to the a t minus t naught times the initial condition x naught. Since this matrix e to the a t minus t naught actually allows us to state the solution to the autonomous system for any initial condition x naught, it is called the fundamental matrix of system 14. And we also write it by the capital letter phi with an index c for continuous time, which we give two arguments, the time t and the initial time t naught. As we shall see shortly, it's actually also relevant for the continuous time state space model, which includes external inputs u of t. By the very fact that the fundamental matrix phi c of t and t naught is defined by the matrix exponential e to the a t minus t naught, it's easy to see that the property stated in proposition 9.11, namely phi c of t and t naught is equal to phi c of t minus t naught and 0 is satisfied. Application 2 of proposition 9.10, which has stated that the resolvent is the Laplace transform of the matrix exponential, is that we can actually use this fact to compute the matrix exponentials via the Laplace transform. So, for example, suppose that we want to compute the matrix exponential e to the at of the matrix A given by this matrix. Then the resolvent of A, Si minus A inverse, can be calculated based on any of the methods that we have seen in chapter 8, so either by using the aggregate matrix or by using the algorithm that follows lemma 8.8. Knowing that the resolvent is the Laplace transform of the matrix exponential, we can take the Laplace inverse transformation of the resolvent to obtain the matrix exponential. And since the inverse Laplace transform of a matrix is given by the inverse Laplace transform of each of its elements, all we need to do is take the inverse Laplace transform of all of the elements of the resolvent here, which is easy to do based on the lookup table. And what we get is the matrix exponential e to the at, which in this case is equal to e to the sigma t times this matrix of cosines and sines of omega t. And if you like, you can check this result against the classical way of computing the matrix exponential e to the at by using the Jordan form. Of course, you will get to the same result as by using the resolvent of A. So far, we've only looked at the solution to the continuous time linear time invariant autonomous system. So now we're also going to look at the more general case of a continuous time linear time invariant state space model. The major difference is, of course, that the state space model also includes an external control input u of t. And Theorem 9.12 states that the solution to this continuous time linear time invariant state space model in the time domain is given by this expression for y of t, which includes the fundamental matrix in the first term and also in the second term inside of this integral. The proof of this formula is actually fairly straightforward. We start with the ODE of the state equation, which is stated here as dd tau x of tau is equal to a times x of tau plus b times u of tau. Now we bring this term over to the left-hand side so that we get to this equation that we may now multiply from the left with the factor e to the minus a tau. And in this place here, we may change the order of multiplication from e to the minus a tau times a into a times e to the minus a tau due to lemma 8.5a. And then it's easily verified by the product rule that this left-hand side here is equal to d tau of e to the minus a tau times x of tau, and we leave the right-hand side unchanged. Next, we integrate both sides of the equation from t0 to t d tau, where on the left-hand side, the integration cancels out with taking the derivative, and we end up with this function evaluated at the upper limit of the integral minus the same function evaluated at the lower limit of the integral. And again, the right-hand side remains unchanged. Next, we bring over this term to the right-hand side and then multiply both sides from the left with the factor e to the at, so that on the left-hand side e to the at times e to the minus at cancels out, and on the right-hand side we have an additional factor from the left of e to the at in front of both terms. By lemma 8.11b, we can actually combine the product of these matrix exponential into the matrix exponential e to the a times t minus t naught. And similarly, we can pull this constant factor into the integral and then again combine the two matrix exponentials e to the at and e to the minus a tau into this matrix exponential. And we've already found the formula that we wanted to prove. After Theorem 9.12 has stated the solution to the continuous time linear time invariant state space model in the time domain, Theorem 9.13 states the solution to the state space model in the frequency domain or in the Laplace domain. The solution provides the Laplace transform of the output signal y of s, and it's given by this expression that consists of two terms. The first term involving the initial condition x0, and the second term involving the Laplace transform of the control input u of s. The factor multiplying the control input signal is given by this expression here, which is defined as the transfer function of the state space model 10, and it's usually denoted by g of s. The proof of this fact is straightforward based on the time domain solution that we have obtained on the previous slides. In fact, all we need to do is take the Laplace transform of the time domain solution of the state x of t, which in the Laplace domain is given by this expression here, where we have used the fact that the Laplace transform of the matrix exponential is given by its resolvent according to proposition 9.10, and we have used the fact that the convolution in the time domain is equivalent to a multiplication in the frequency domain according to Theorem 9.7d. In order to get from the Laplace transform of the state x of s to the Laplace transform of the output y of s, all we need to do is apply the output equation, which is simply given by y of s is equal to c times x of s plus d times u of s. And if we now substitute this formula here, we get exactly to our solution formula up here.